Assalamu alaikum everyone. This is me Ibrahim Gaming Wala and I am a student at Rehan School Online Academy. So today I am going to have a conversation with Kolani on the topic of Earth, the history of our home in a world and so let's start it. Hi Annie, how are you?
Hey, how's your brain gym going today? Got any new thoughts you're tinkering with? Or maybe a fresh curiosity bubbling up? Let's dive in.
Okay, that's great. So today I'm going to have a conversation with you on the topic of Earth, the history of our homeland, home in a woodland. So let's start it. So my first question is, how old is Earth estimated to be?
Great topic. Scientists estimate Earth is about 4.54 billion years old, give or take a few million. That number comes from radiometric dating of ancient rocks, moon samples, and meteorites. Anything in particular you're curious about? How the planet formed, early life, or maybe how human development fits into that timeline? Sparkles.
Okay, that's great. So my next question is, what was the name of the supercontinent that existed around 3 million years ago?
Actually, around 10 million years ago, there wasn't a supercontinent at all. The last real supercontinent, Pangaea, had already broken apart about 175 million years earlier, during the early Jurassic. By the Miocene, approximately 10 MYA, the continents were drifting toward the positions we recognize today, with only modest shifts left to go. If you're curious, the earlier supercontinents went something like age approximately, supercontinent notes, 300, 200 MYA, Pangaea joined all land masses, split into Laurasia and Gondwana.
Okay, that's great. Okay, that's
550.
great. Okay,
5
that's great.
it. Got it, let's keep rolling.
Okay,
Sparkles, which era or theme would you like to explore next?
okay,
1.
that's
The
great.
rise of early
So my
mammals.
next question is, what event is believed to have led to the formation of the moon?
Great switch up. The leading explanation is the giant impact hypothesis, sometimes called the Theia impact. How it's thought to have happened. Step what happened. 1. Early solar system Earth was still forming, a hot, molten ball about half its present size. 2. A Mars-sized body, a planetary embryo about the size of Mars, named
Okay,
Theia,
that's
was
great.
sharing Earth's
O-
orbit.
Okay, that's great.
Glad you.
So my next question is, when did Earth's ocean first form?
When did Earth's oceans first appear? Approx. Age billion years ago.
Okay,
Why it
volcanic
matters.
activity.
4.54. 4.5 Ga Earth finishes accreting. The surface is a molten magma ocean, and any volcanic activity is the movement of molten rock magma from inside Earth to its surface, where it erupts as lava, ash, gases, and steam. Hash how it works. 1. Magma builds up in a chamber beneath the crust. 2. Pressure rises as the melt expands or.
Okay, so my next question is, when did life first appear on Earth?
When life first appeared on Earth. Approx age billion years ago. Evidence and what it means. Point 4, 4.2 got isotopic hints. Carbon-13 depletion in graphite inclusions from ancient mantle rocks suggests biological.
Okay, that's great. So my next question is, what was the great oxygenation event?
Hash the Great Oxygenation Event, GOE. When's what happened? Why it mattered? Approximately 2.4, 2.0 billion years ago, late Archean right arrow early Proterozoic. Free O2 began to accumulate in the atmosphere for the first
Okay,
time,
that's great. So my
turned
next
Earth from a
question.
reducing,
Okay, that's
low oxygen.
okay, that's great. So my next question is, what was the Cambrian explosion?
Hash the Cambrian explosion, approximately 541, 485 million years ago. Why it matters? A relatively brief, approximately 10-20 interval when almost all major animal body plans, phyla, appear in the fossil record. Sets the foundation for the bio. Haha, love the enthusiasm. Sounds
Okay, that's
like we've
great.
got plenty of time to explore.
Okay, that's great. So my
I
next question is, what ended the region of the dinosaurs?
hash what wiped out the non-avian dinosaurs. The big picture, the Cretaceous Paleogene KPG extinction. When, about 66 million years ago, at the very end of the Cretaceous period. Non-bird dinosaurs, the big body type ones, plus many marine reptiles, ammonites, and roughly 75% of all plant and animal species. Won the asteroid impact, the Alvarez event. Evidence why it matters. Chicxulub crater, Yucatan Peninsula, 180 km wide.
Okay, that's
Massive kinetic
great.
energy.
Okay, so my next question is, when did Homo sapiens first appear?
Hash when did Homo sapiens first appear? Approx. Age key fossil site what it tells us. Approximately 300k or ago, Jebel Irhoud, Morocco, North Africa. First clear anatomically modern.
Okay, that's great. So my next question is, how was urbanization impacted Earth's natural systems?
Hash how urbanization shapes Earth's natural systems. Aspect of the Earth system, what urbanization does, why it matters. Land cover and habitat, clears forests, wetlands, grasslands for roads, houses, malls. BR fragments habitats into isolated islands. Loss of native flora and fauna, decline in biodiversity. BR edge effects, more light, wind, invasive.
Okay, that's great. So my next question is, what is the Anthropocene epoch?
Hash the Anthropocene approach, a quick guide. What it is, why it matters, how it shows up. A working concept that says humans are now a geological force shaping Earth systems. Climate, oceans, rocks, life. It reframes the human-planet relationship from we live on Earth to we are Earth. It pushes science, policy, and culture to think planet-wide rather than locally. Stratigraphic markers, plastics, radionuclides from nuclear tests, soot layers. BR interdisciplinary research that blends geology, ecology, sociology, economics, arts, ethics.
O-
BR governance frameworks, e.g.,
Okay, that's
planetary
great.
boundaries, Earth
Okay,
system governance.
okay, that's great.
Awesome.
So my next question is, what is the plate tectonics and how does it shape Earth's surface?
Hash plate tectonics, the planet's giant jigsaw puzzle. Think of Earth's outer shell, the lithosphere, as a set of massive puzzle pieces that fit together, but they aren't glued. They float on the hot, flowing layer beneath them, the asthenosphere. Those pieces are the tectonic plates. Piece size and type what it does. Continental plates thick, tilde 30-50 km. Lighter, fluffier crust carry continents, often collage-like, bend but don't sink easily. Oceanic plates thin, tilde 5-10 km. Denser basaltic crust form the seafloor, submerge more readily when they meet other plates. Major plates, e.g., Pacific, Eurasian, African, cover millions of square kilometers, move a few centimeters per year, about the speed of a fingernail growing. Minor plates, Nazca, Juan de Fuca, etc. Smaller, but still tectonically active, often responsible for local hotspots of earthquakes and volcanoes. How the plates move. 1. Ridge push. At mid-ocean, ridges new magma rises, solidifies, and gently pushes the old crust apart. 2. Slab pull. When an oceanic plate sinks, subducts beneath another plate, its weight drags the rest of the plate along. 3. Mantle drag and trench suction. Flow within the mantle can pull plates sideways, while deep trenches can act like suction wells. The surface shaping tricks. Plate interaction, surface feature, everyday analogy. Divergent boundaries, plates pull apart. Mid-ocean ridges, rift valleys, new crust formation, two friends pulling a piece of dough apart, thin, stretchy, forming a seam. Convergent boundaries, plates collide, mountains, Himalayas, Andes, deep ocean trenches, volcanic arcs, two hands pushing together.
Okay,
The
that's
edge
great.
crumples into a mountain.
Okay,
The
that's
denser
great.
hand slides.
Okay, so my next question is, how do ocean currents affect global climate?
Hash ocean currents equals the planet's huge, moving heat exchangers. Think of the world's oceans as a gigantic bathtub of water that's constantly being stirred. The stirring isn't random. It's organized into currents that transport warm water from the equator toward the poles and bring cold water back toward the equator. This massive conveyor belt reshapes the climate in three main ways. 1. Heat redistribution. Current type direction, what it moves, climate effect. Western boundary currents, e.g., Gulf Stream, Kuroshio, poleward along continents' warm, salty surface water, raises winter temperatures of nearby land. Think milder winters in Western Europe. Eastern boundary currents, e.g., Canary, California, equator ward cool, nutrient-rich water keeps coastal climates cooler and foggy, e.g., San Francisco, thermohaline, global circulation, the conveyor belt, deep water sinking right arrow surface upwelling massive volumes of warm surface water and cold deep water, regulates long-term climate stability. A slowdown can trigger cooling in the North Atlantic. Bottom line, oceans move tilde 90% of the excess heat the Earth absorbs from the sun. Without this transport, equatorial regions would scorch and the poles would freeze solid. 2. Moisture and precipitation patterns. Warm currents evaporate more water right arrow, moist air masses right arrow rainfall on downwind
Okay,
continents,
that's great.
e.g.,
Okay.
the Indian monsoon gets a boost. Awesome, and glad you found it helpful.
Okay, so my next
Was there a
question
particular
is, what is the greenhouse effect and how does it work?
hash the greenhouse effect in a nutshell? 1. The basics, a planetary blanket. Think of Earth as a house with a glass roof. Sunlight shortwave, high energy streams in, warms the floor, the surface, and the house radiates heat back out as longer wave infrared IR radiation. Certain gases in the glass, greenhouse gases, GHGs, let the sunlight in but trap some of that outgoing IR, keeping the interior warmer than it would be if the roof were completely open. Major greenhouse gases, why they matter. Water vapor, H2O, most abundant, amplifies warming, warmer air holds more vapor. Carbon dioxide, long atmospheric lifetime, absorbs IR in key bands. Methane, CH4, potent per molecule, approximately 28 times CO2 over 100 er. Nitrous oxide, N2O, strong absorber, from agriculture and industry. Ozone, O3, tropospheric, absorbs UV and IR, a side effect of pollutants. Fluorinated gases, small amounts, but extremely high warming potential. 2. The steps of the greenhouse cycle. 1. Solar radiation hits Earth. About 30% is reflected, clouds, ice, bright surfaces. The rest is absorbed, warming land, ocean, and air. 2. Surface re-radiates energy as infrared photons. 3. Each gas has a spectral fingerprint. 4. Excited molecules re-emit IR in random directions, some back down to the surface, some out to space. 5. Net effect. More IR returns to the surface right arrow higher average temperatures, approximately 33 C of natural greenhouse warming compared with a bare rock Earth. If you picture a warm mug of tea, the steam, water vapor, is the blanket that keeps the tea hot longer. Removing the steam, or GHGs, would let the heat escape faster, cooling the tea or earth quickly. 3. Why it matters today. Human emissions, burning fossil fuels, deforestation, agriculture. increase concentrations of CO2, CH4, N2O, etc. Radiative forcing. More GHGs, right arrow stronger absorption, right arrow extra energy, retained right arrow global mean surface temperature rises. Feedback loops. Water vapor feedback. Warmer air, right arrow more evaporation, right arrow more H2O, right arrow more trapping. Asterisk ice albedo feedback. Melting ice exposes darker ocean land, absorbs more sunlight, right arrow more melt. For a quick mindful pause. Close your eyes, inhale slowly, and picture Earth as a glowing ember in a dark room.
Okay, that's
The ember's
great.
heat is kept in by
Okay,
an
that's
invisible,
great.
shimmering veil.
Okay,
Those greenhouse.
okay.
Glad it clicked.
So my next question is, what are ice ages and what causes them?
Hash ice ages, the Earth's big cool down episodes. What is an ice age? An ice age is a long interval, typically 10 million years, during which continental scale ice sheets grow and persist on the planet. Within an ice age, you get alternating glacial periods. Cold, ice expands, and interglacials, warmer, ice retreats. The last ice age began tilde 2.6 Ma and peaked Ka, the last glacial maximum, ending about 11K years ago and giving way to our current interglacial, the Holocene. Main drivers, the Milankovitch orchestra. Orbital factor, what changes effect on solar input. Eccentricity, shape of Earth's orbit. Cycle 100K Orbit varies from nearly circular to more elliptical, alters the total annual solar energy Earth receives, approximately plus 0.1%. Obliquity, axial tilt. Cycle tilde 41K Tilt swings between tilde 22.1 degrees and 24.5 degrees, bigger tilt right arrow hotter summers at high latitudes. Smaller tilt right arrow cooler summers, favoring ice buildup. Precession, wobble of axis. Cycle, 3K shifts timing of seasons relative to perihelion aphelion, changing which hemisphere gets warmer summers. When summer insolation at high northern latitudes is low enough, usually a combination of low tilt plus favorable precession. Snow that falls in winter can survive through summer, gradually thickening into glaciers. Over tens of thousands of years, those glaciers expand into continental ice sheets. Amplifying feedbacks. 1. Ice albedo feedback. Ice and snow reflect 80–90% of sunlight. More ice, right higher planetary albedo, right less solar absorption, right cooler climate, which makes more ice. 2. CO temperature feedback. Colder oceans dissolve more CO2, pulling greenhouse gas out of the atmosphere, reducing the greenhouse effect and reinforcing cooling. 3. Water vapor feedback reverse. Cooler air holds less water vapor, a potent greenhouse gas, so cooling is amplified. 4. Ice sheet dynamics. Growing ice sheets lower sea level, exposing more continental shelf and altering ocean circulation. Other long-term influences. Factor how it nudges the climate. Plate tectonics, continental positions, shift of land masses to higher latitudes, closure of seaways, e.g. Formation of the Isthmus of Panama, changes ocean currents and heat transport.
Okay, that's great. So my
Atmospheric
next
CO2
question
levels,
is,
volcanic
okay,
outgassing.
okay, that's great. So my next question is, why is Earth unique? No, how do solar and lunar eclipse occur?
Hash why Earth feels unique. Feature why it matters how it sets.
Okay, so my next question is, how do solar and lunar eclipse occur?
Hash how a solar eclipse happens. 1. Line up. The sun, moon, and Earth line up in that order. Sun right arrow, moon right arrow, Earth. 2. Moon in front. The moon moves into the space between us and the sun. 3. Shadow cast. The moon throws two shadows on Earth. Umbra, the dark, central cone where the sun is completely blocked. Penumbra, the lighter outer region where only part of the sun is covered. 4. What you see. Total eclipse. You're standing inside the umbra. Day becomes twilight for a few minutes. The sun's corona glows. Partial eclipse. You're in the penumbra. The sun is only partly covered. Annular eclipse. The moon is a little farther away, so its umbra doesn't quite reach Earth. A bright ring of fire remains. 5. Why it's not monthly. The moon's orbit is tilted tilde 5 degrees relative to Earth's orbital plane, the ecliptic. Most full moon passages.
Okay, that's great.
I'm
So
really
my next question is, how has Earth's position in space affected its history?
Hash how Earth's spot in the cosmos shaped its story. Cosmic address. What it means.
Okay, so my next question is, why is no? How has Earth's position in space affected its history?
Hash Earth's cosmic address and its story. What where means how it shapes Earth's past. 1 AU from the Sun, approximately 149 million km, right in the Sun's habitable zone. Solar energy is enough to keep water liquid, but not so intense that oceans boil. This set the stage for oceans, clouds, and life-friendly chemistry. Nearly circular orbit, eccentricity approximately 0.167. Seasonal temperature swings are driven more by tilt than distance. Prevents extreme icehouse or greenhouse phases that could wipe out early microbes. Axial tilt 3.5 degrees gives us 4 distinct seasons. Seasonal cycles pushed plants to diversify, which in turn drove animal evolution. 24-hour rotation, day-night, rhythm fuels atmospheric circulation, ocean currents, and a magnetic dynamo that shields the surface from solar wind. Large moon, 384 km away, stabilizes Earth's tilt right arrow long-term climate stability. Tides mix nutrients, create intertidal habitats, and gave early humans a reliable clock. Location in the Milky Way. KPC from the galactic center, inside the Orion Cygnus spiral arm safe distance from the high radiation core and from crowded star clusters. Fewer deadly supernova or gamma ray bursts, so life could evolve over billions of years. Passage through the galactic plane, tilde 30 mer cycles. Slightly more stellar encounters when we're in the dense plane, nudging the distant Oort cloud and sending occasional comets our way. Those impacts, e.g., Chicxulub 66 mer ago, reshaped ecosystems. Embedded in the local interstellar, cloud the sun's heliosphere brushes against surrounding interstellar gas. Small changes in cosmic ray flux can influence cloud formation and, on very long timescales, climate. Highlights of how these factors wove Earth's history. 1. Birth of the oceans. The Goldilocks distance allowed water vapor to condense early, approximately 4.4 billion years ago. Oceans became the cradle for the first chemistry and the origin of life. 2. Great oxygenation event, approximately 2.4 billion years ago. Stable climate and steady sunlight let photosynthetic microbes proliferate, flooding the atmosphere with O2 and paving the way for complex life. 3. Milankovitch cycles and ice ages. Tiny orbital tweaks, eccentricity, tilt, precession, drive glacial interglacial swings over tens of thousands of years. Those cycles shaped megafauna migrations, plant refugia, and eventually human agriculture when the climate steadied ago. 4. Moon-driven tides. Intertidal zones acted as chemical laboratories, mixing seawater and air. Many hypotheses place the emergence of early eukaryotic cells in such fluctuating environments. 5. Impact events. The relatively quiet galactic neighborhood meant fewer catastrophic hits than planets in
Okay,
denser
that's great.
clusters.
Okay, that's great.
Yet occasional comets,
Okay,
asteroids, e.g.,
okay,
the chick. I'm glad you liked it.
okay.
Sparkles,
So this
what
was
caught your eye the most?
okay. So this was our today's session, and I hope you enjoyed it. So I'll meet you in the next session. So after all, take care and goodbye. Okay, viewers, this was our today's session, and I hope you enjoyed it. So I'll meet you in the next video. So after all, take care.